Ben Martinez with the Forest Service, and along with the Mineral Resources Program with the USGS, funded this work. I'd like to thank Mountain Studies Institute for the opportunity to discuss our Helicopter-Borne electromagnetic survey over the Bonita Peak Superfund area in Silverton, Colorado. And I'd like to acknowledge our co-authors, especially Ben Martinez with the Forest Service, and along with the Mineral Resources Program with the USGS, funded this work. We have two-part goals of this study. From a modern hydrogeologic perspective, we want to image groundwater aquifers and characterize the electromagnetic EM response of quaternary sediments and bedrock lithologies, and integrate EM and hydrogeologic data to better understand the Chattanooga-Fenn wetland system. And from an ancient hydrothermal system perspective, we'd like to characterize EM responses of vein structures, caldera faults, and hydrothermally altered rocks, and use the EM data to inform us about the hydrothermal plumbing system responsible for mineralization. This conceptual hydrogeologic model shows well the complexity of what we're trying to image with geophysics. This is a terrain image with alteration draped on terrain. There's Cement Creek in the lower left, and we're looking at Prospect Gulch. The rocks in green are weakly altered, and those rocks are overprinted by rocks in red, blue, and yellow with more intense alteration that have associated clay, minerals, as well as sulfides, especially pyrite that weathers to produce acid rock drainage. On the lower right-hand side of the diagram, we have shallow fractures depicted at the surface. Those fractures get more sparse with depth. We have the small green arrow is shallow groundwater. The large green arrow is deeper groundwater. We have igneous intrusions. The red arrow indicates hydrothermal fluids that are precipitating minerals along vein structures shown in red and yellow. Then we have brown, which represents mine tunnels that intersects the groundwater table, causing the water to be short-circuited and come out to the surface. And then we have mine waste piles at the adits. So we have a lot of complexity that our EM data is trying to image. In April, May of 2019, Geotech, a geophysical contracting company, flew a geophysical survey over the study area. The yellow lines are flight lines of the survey, with a core area having more widely spaced lines, and then a focus areas, which the red outline is one of the focus areas of Upper Mineral Creek Basin, which has more densely spaced flight lines that allow for more detailed imaging of the subsurface. The outline in blue is the Chattanooga-Fenn, and at the left is the helicopter that is towing the equipment that acquired the EM data. I'd like to give you a geologic overview of the Upper Mineral Creek Basin study area. And the rocks here are typical of what we find in the Southern Rocky Mountains volcanic field. The rocks labeled TSJ in the Geologic Map are older volcaniclastic intermediate composition rocks that are overlain by ash flows in green derived from western San Juan Mountains calderas. Mineral Creek roughly parallels the structural margin of the Silverton caldera, and to the east of Mineral Creek, the unit TSV are Silverton volcanic intermediate composition lavas that infilled the caldera complex. The units labeled TI are igneous intrusions that occurred throughout the basin. And all of these rocks in the geologic map were altered due to hydrothermal alteration to a secondary alteration assemblage, and that's shown in the alteration map to the right. The rocks that are weakly altered are in green, and they're weakly propylatized. And with increasing intensity of alteration, we have in blue weak sericite pyrite, in orange quartz sericite pyrite, and the unit in labeled PRAS in pink is mixed propylitic acid sulfate. And the blue polygon is the rough outline of Chattanooga Fen. And I'll be discussing two geophysical resistivity depth profiles, one an east-west profile and another a north-south profile. Here's a bird's eye view of upper Mineral Creek Basin, and it shows well where fens tend to occur, which is at the base of mountain slopes. And Chattanooga Fen, labeled CF here, is no exception. It is exceptional in that it's an iron fen, which is relatively rare, and its iron source is probably weathering of the QSP alteration that's prevalent in the vicinity of the fen. This diagram shows the ranges in resistivity that we'd expect to see in our study area for the rocks that occur there. And in the lower part of the diagram is a bulk resistivity scale in kind of rainbow colors, from red being less resistive and blue being very resistive. And this is the actual range of lithologies in our study area. In the upper right, igneous metamorphic rocks, they tend to be very resistive. But in the middle top, the igneous rocks that are weathered tend to be less resistive. And below that, the clays and when there's QSP alteration and clays introduced, you can also have less resistive lithologies. The pore water also influences resistivity with increasing dissolved constituents from acid rock drainage. You can get a decreasing in resistivity. Now I'd like to discuss the west to east resistivity depth profile. And this images to greater than 300 meters depth. And the profile starts just outside of the watershed boundary on the west. It traverses the Chattanooga Fen, and then it trends toward Ohio Peak on the east. What you notice right away is the striking contrast in resistivity, and the west part of the profile, west of Mineral Creek, greater than 100 meters. The rocks are very resistive, and this is characteristic of the San Juan Formation volcaniclastic rocks. We notice a very thin, shallow, low resistivity zone centered about where the arrow is over Mineral Creek, and we attribute this to weathering of the quartz sericite pyrite alteration type on either sides of Mineral Creek. And some of this we think is responsible for the high iron contents that are weathering into the Chattanooga Fen. Beneath the thin low resistivity zone is a thicker low resistivity layer, and this is continuous into this really large low resistivity zone below the word Ohio Peak. And we attribute this to clay minerals that are associated with the quartz sericite pyrite alteration type. As we head toward Ohio Peak, we know there's an acid sulfate system with silicification near the peak, and this is a higher resistivity area centered over Ohio Peak. And then beneath it, there's a low resistivity zone labeled H, and we attribute this to clay minerals that are associated with the acid sulfate system. Further to the east, we have a lens of low resistivity that we attribute to possibly higher TDS in groundwater that's in a lava permeable facies that accumulated within the volcanic pile. Now I'd like to discuss the north to south resistivity depth profile, which images to greater than 300 meters. The profile starts just north of the watershed boundary and then trends southward west of Mineral Creek, past Middle Fork Mineral Creek. I'd like to start by discussing the north part of the profile. The tabular low resistivity feature labeled A we attribute to stored mountain block water that is stored near the interface of bedrocks and superficial deposits. Southward, this feature labeled B we interpret as a groundwater divide. And then there's another low resistivity lens labeled C beneath Mill Creek that we attribute to weathering of the quartz-aracite pyrite alteration that's prevalent near the outlet of Mill Creek. Further south, we have a lens-shaped low resistivity body that we think is stored mountain block water that's derived from weathering of quartz-aracite pyrite that's prevalent along the slopes south of Mill Creek and west of Mineral Creek. Another way of looking at the EM data is in depth slices. So here we have a map view of the EM data at different depths. On the left we have depths of 0 to 4 meters, and on the right we have depths of 279 to 309 meters. And what I'd like to draw your attention to in the 0 to 4 meter depth slice is the area around Chattanooga Fen. It has a fairly prevalent area of low resistivity that occurs all along the fen and south of the fen. And then east of Chattanooga Fen, there's low resistivity areas on the lower slopes below Ohio Peak. And then in contrast, on the 279 to 309 meter depth slice, you see how much more resistive that the terrain becomes west of Mineral Creek, with the San Juan Formation volcaniclastic rocks being very resistive at this depth. The area around Chattanooga Fen becomes slightly more resistive. However, that area of low resistivity labeled C here is associated with the quartz-aracite pyrite alteration type, and it gives us a sense of the geometry of clay minerals that are associated with this alteration. We're beginning to integrate the Hydrologic Tracer inflow data. This is from 1999 data, along with our EM data, and this is the 0 to 4 meter depth slice. And on the left, we have manganese in micrograms per liter, and they're in the area around Chattanooga Fen has very high manganese, I should say, concentrations as high as 7,300 micrograms per liter. And this is consistent with low resistivity signatures in the shallow EM data. And that also corresponds with acidic conditions in inflows in this reach as well. Rob Runkle did reconnaissance mapping in June of 2020 and identified several seeps and springs. Some of them have visible iron precipitation, and this particular seep on the left is flowing into this pond. So these types of features that we're seeing on the ground is also consistent with our EM signatures of being low resistivity. We're beginning to bring together the depth slices and the conductivity depth profiles into a 3D geophysical model. And this allows us to interpret the geophysical response of adjacent areas at a basin scale. to allow us to make better interpretations about the groundwater and then the hydrogeologic conditions that cause our EM signatures. So in summary, from a modern hydrogeologic perspective, we've imaged possible groundwater derived from altered volcanics that may feed the Chattanooga Fen and other areas, and have identified possible source areas of acidic drainage. We've imaged geometry of low electrical resistivity from groundwater features, and they may be important for mountain block water storage. And from an ancient hydrothermal system perspective, we've imaged subsurface electrical resistivity at the basin scale, and have imaged the geometry and resistivity of altered areas important for mineralized systems. And we've also probed the caldera structural margin having variable permeability and resistivity. Thank you.